Okay, so this setup here, we've got two particles, A of mass 3, B of mass 7. Initially they're at rest, but I think that A is projected towards B with speed 4, it says. So B stays at rest, but if that's going towards B, they're going to collide. And then it says they coalesce to form one particle. Coalesce means they stick together, so they won't separate. So you can see, you can write it as one particle, the combined masses. And then first part then says write down the coefficient of restitution between the particles. Remember, coefficient of restitution is just the E value, yeah? And that's calculated by looking at the speed of separation divided by speed of approach. If you think about it, after the impact, speed of separation, well, they don't separate, don't they? Okay, they stick together. So there's no separation. So that means the speed of separation is going to be 0. So if the speed of separation is 0, E is actually going to be 0. Simple as that. Okay. 2 then, determine the speed of the combined particles after the collision. Okay. Well, we could do that, of course, by looking at the conservation of momentum. Okay. Of course, with the conservation of momentum, the total momentum before equals to the total momentum after. Okay, so the total momentum before will be mass times velocity, 3 times 4, plus then the mass times velocity there, so 7 times 0, and that will equal then the combined masses, which is 10, times then the combined speed, okay, because they're going at the same speed, v. So that will be 12, plus 0 is 12, and that'll be 10v, so v will be 12 divided by 10, which is 1.2 meters per second, okay. Part B there, okay, so part B, it says you've got another particle of mass 6 kilograms travelling with speed 5 meters per second, collides directly with a vertical wall and rebounds. Okay, so this is the setup here. It's going towards a wall, rebounds. Coefficient of restitution between the particle and the wall is 0.25. So we know in this case for part B, E is 0.25. Calculate, it says then, part 1, the speed of the particle after the collision of the wall. So remember, E is equal to speed of separation divided by speed of approach. Okay, so we know E is 0.25. Speed of separation when it's after it's hit the wall, when it's separating from it, is going to be V. It's just going to be V, isn't it? It's not going to be VB minus VA, because the wall is just locked in place, right? So, you know, that's got no speed. So you're just interested in this, in terms of speed of separation, you're just interested in the speed of this object here, okay, moving away from the wall. And of course then, speed of approach, what is this approaching the wall at? 5, yeah? So you get that. And then all you got to do then, take the 5 over, times by 5 to get your V. So that implies then V is 1.25 meters per second, okay? Find the impulse then, it says exerted by the wall on the particle. So remember, the impulse, okay, the impulse on the particle will equal to the change in momentum, okay, of the particle. So the particle's momentum will change because it'll be transferring some momentum over to the wall. The wall will be absorbing, of course, the wall isn't going to move, it'll be absorbing the energy. So the momentum, change of momentum will be the momentum after, yeah? Take away the momentum before. So the momentum after will be the mass, which is 6, times the velocity, which will be, we worked out to be 1.25. But remember, it's going in that direction, yeah, the velocity, so we need to put minus 1.25 if we take this as positive, okay, correct, so you need to put minus 1.25 there because it's going the opposite of positive. Take away then the mass, which is 6, times that velocity there, which is 5, and that's going in the positive direction. So we get minus 37.5 Newton seconds. Okay, the magnitude, the impulse, okay, will equal to 37.5 Newton seconds.